Hi everyone, so here we are on chapter 7, day 3, and today we are going to talk about periodic trends. So the first periodic trend we are going to discuss is ionization energy. So you should know the definition of the term. So it means the energy required to remove an electron. Let's take a look at this chart. This chart is talking about ionization energy. So here we have I1, I2, I3, so on and so on. So I1 is the amount of energy to remove the first electron. I2 is the amount of energy to remove the second electron. And then this would be the amount of energy to remove the third electron, so on and so on. All right, so we're going to start with sodium. Sodium is in group 1. Notice we're going to be moving across in period 3. We're going to see what happens here. So the first electron from the outermost energy level is removed, and it requires this much energy. Now look at the huge jump in energy as we try to remove the second electron. Okay, let's see if this makes sense. So think about what happens to the size, what happens to the size of the atom when it loses an electron. All right, so let's just draw a picture so we can sort of have a visual here. So sodium, originally, let's just say sodium is like this big, okay? Now, if we remove an electron from sodium, okay, now you have more protons than electrons, so that means that the remaining electrons are going to get pulled in tighter. Okay, so it gets smaller in size. All right? Then, if you try to remove another electron, then it's going to get even smaller in size. It gets smaller and smaller in size, all right, every time you remove an electron. And that's because the nuclear charge, remember, the nuclear charge is what is found in the nucleus. Okay, every time you remove an electron, that's a positive sign. Every time you remove an electron, the nuclear charge will get stronger and stronger and stronger, pulling in the remaining electrons in tighter. All right? Now, if you also recall sodium, since it's in group 1, it wants to lose one electron, right? So it'll lose one electron to be more stable like a noble gas, but it doesn't really want to lose a second electron. Okay? So notice it's going to fight a little harder to keep that electron. That's why it increases significantly in ionization energy. All right, now let's take a look at magnesium, which is in group 2. Well, what charge does magnesium like to form? A +2 charge. So it wants to lose 2 electrons. Okay, it loses its 2 electrons, but it doesn't want to lose the third. All right, look at the huge jump there in energy. All right, so then I hope you can kind of see a pattern here. So once you see this ginormous jump, okay, you should start to think about whether or not it is stable in terms of the number of electrons that it contains. All right, once it contains the stable amount of electrons, it's really going to try to hold on to those electrons very, very, very tightly. It doesn't want to give them up. All right, notice here it says core electrons. The core electrons, remember, are the electrons in the inner energy levels. So it says that the large jump in ionization energy and going from removal of valence electrons to removal of core electrons. All right? So that's why there's a huge jump. You're trying to remove core electrons now, and it doesn't want to give up those core electrons. All right? The nuclear charge is pulling strongly on them and doesn't want to give them up. All right, so our periodic trend for ionization energy, and it says first ionization energy, meaning it's the amount of energy to remove the first electron. All right, so you should know these trends. If you remember the ionization energy one, it decreases going down. Remember di going down? Di represents decreasing ionization energy. So di going down, because when you die, you get buried underneath the ground. So if you remember that, di going down, that will help you. and then therefore as you move across the periodic table, it increases. Okay, increases going across. So the reason why, you should understand and be able to explain the reasons why it gets bigger and why it gets smaller. All right, so first let's talk about as it's going down, it decreases in ionization energy, meaning it's easier to remove an electron. It's easier to remove an electron as you go down, because if you remember the size of the atom, it's much bigger in size as you go down a group. But your ionization energy will increase moving across, meaning it takes more energy to remove an electron as you move across the periodic table because it's much smaller in size. So if it's smaller in size, that means that the nuclear charge is much stronger. It's really pulling in those electrons tightly and doesn't want to give them up. If it's large in size, the nuclear charge is not as strong. All right, so it's easier to remove an electron. All right, so this is also ionization energy. And if you look at this chart, you'll notice at the peaks, okay, where are all those elements found? All right, those are all your noble gases. So notice that your noble gases, right, will require the most ionization energy. The most ionization energy because they are not only very small in size, but they are also already stable. They do not want to lose any electrons. And then let's look at the bottom. Oops, pen. Let's look at the bottom here. What do you notice about these elements? All of those elements are found in group 1, right? Group 1. Those are your alkali metals. So those are the ones that are going to be the easiest to remove electrons from. They are larger in size, right? Which means the nuclear charge is weaker, therefore much easier to remove an electron. And plus, your alkali metals, they want to lose an electron, okay, to be more stable like a noble gas. This table is just showing you the ionization energies of the alkali metals and the noble gases. So you can see going down the group, right, going down the group, right, even going down this group, ionization energy decreases. Remember, dye going down, okay? But if you're comparing these ionization energies, you can see that these are much, much smaller than your noble gases. Once again, the noble gases, they're very small in size, and not only are they small in size, but they are also already stable, and they have a very strong nuclear charge. So they do not want to give up their electrons very easily. All right, electron affinity. So electron affinity, the energy associated with the addition of an electron. So it's very similar to electronegativity. Okay, so the amount of energy to gain an electron. All right, so then let's talk about electronegativity. Once again, you should know the definition. Okay, an element's ability to gain electrons, or what we like to say, to attract electrons to itself. You should remember that fluorine is the most electronegative element. All right, so if we look at a periodic table for the trend, increases across and then decreases going down the group. So if you remember that fluorine, and fluorine's over here on this side, if you remember that fluorine is the most electronegative, then that's how you know it has to increase towards fluorine, and then therefore it will decrease going down. Okay? Also remember, on this side of the periodic table are the elements that will typically form a negative charge. So they want to gain electrons in order to be stable. So that's why electronegativity, its ability to attract electrons, all right, increases moving towards the right. All right, the last trend that we are going to talk about is size, or what we call atomic radii. Radii is plural for radius. So remember, if we have two atoms side by side, we measure the distance between the nucleus here and the nucleus there. All right, so this is a radius and that's a radius. So we call that radii, and that's how we measure the size, from center to center. So your trend for size, all right, so let's draw it out. All right, so size gets bigger going down, okay, increases going down, and then therefore decreases going across. All right, and you need to understand that the reason why it gets bigger going down, don't forget there's this concept called the shielding effect. Okay, as you go down a group, the shielding effect will increase as you go down. All right, so remember, shielding effect has to deal with, let me change a color pen here. So shielding effect has to deal with, well, this is your nucleus, right? It has a positive charge, and we have all these energy levels. Okay, as you go down a group, you keep adding on energy levels, right? As you go down a group, you keep adding on rings. Okay, so that means that you will have more inner electrons every time you add on a ring. Okay, so these energy levels and these electrons are making a shield so that the outer electron is being blocked. All right, so this nuclear charge, right, is being blocked or shielded by these inner electrons. So it's a lot harder for the outer electron to be attracted to the nucleus. And that's why it's bigger in size. Since it has very little attraction to the nucleus, okay, or the nuclear charge there, then that's why it's just hanging out. All right, and that's why it's bigger in size. It's not pulled in as tightly. Whereas we move across the periodic table, the shielding effect remains the same. It remains constant moving across. So as you're moving across the period, you're adding on a proton. You're adding a proton, right? And that electron is being added also, but it's being added to the same energy level, all right, as you move across the period. So the nuclear charge is getting stronger as you move across. Therefore, a stronger nuclear charge is pulling in all of the electrons in much tighter, and that's why they are smaller in size. So here's a picture showing you the size. So this will be really good to remember this picture and what's happening to the size. Okay? So as you move across, notice that it gets much smaller. So if you imagine throwing like a ball across the room, it looks like, from your point of view, that it's getting smaller and smaller in size. Size is getting bigger as you go down because we talked about the shielding effect, adding on more energy levels and increasing that shield. And then if you look up, imagine a ball falling down from the sky towards your face. So it appears that it's getting bigger and bigger as it's approaching your face. So that is one way you can remember the size. All right, you also need to make sure you just know the different special names of groups on the periodic table. All right, remember group 1, those are the alkali metals. Group 2, the alkaline earth metals, transition metals in the middle there. Group 7, halogens. Group 8, noble gases. The last two rows, we call these the inner transition metals or the rare earth metals. Okay? You can also see from this picture here, the periodic table is made up of mostly metals. All right? Mostly metals. These are all metals, those are metals. And then your non-metals are a very small portion, and then those are your metalloids right there. All right, so that is everything that you need to know for Chapter 7. And we are finally done, and I will see you later. Bye.